see what time is it. So yesterday we concluded the introduction of the possible representation of the attitude matrix. So I just replied regarding question regarding the quaternions, but I will provide further details in order to have a clearer idea on how to design a matrix. So an attitude matrix. So if you remember correctly, yesterday I showed you this form of the attitude matrix with respect to the quaternion. So I assumed that you are familiar with that matrix, but if you are not, so if you don't know how to determine the attitude matrix from the quaternion to this one, to this expression, this is directly related to the Euler's theorem. So the Euler's theorem of rotation. Euler did a lot of theorem, but it's the Euler's theorem of rotation. So it is basically the representation of the attitude matrix by using the instantaneous axis of rotation and the rotation from one reference frame to the other one. So here yesterday I tried to improve a little bit what I drew yesterday. So if you have the two reference frame, so assuming that you don't need to know the different position of the two reference frame, you are only trying to determine the relative orientation. So 1, 2, and 3 is the inertial reference frame. The UVW is our body frame, for example. You can indeed find an axis of instantaneous rotation E, that is written afterwards as EX, EY, EZ, that basically give you the possibility to rotate one reference frame on top of the other one with an angle that in the slides is called delta theta. Yesterday I called here alpha because here is called alpha, but in the next slides is called delta theta. So what you can do is to write the attitude matrix with respect to this E, so this versor of instantaneous rotation that is equal to EX, EY, EZ, and a certain angle delta theta. So basically you have that this versor here is EX, here this one is EY, and EZ. And you have also the angle delta theta. So the Euler theorem of rotation says that the attitude matrix is equal to the cosine, so the cosine of, so let me write using text box, so it will be a little bit faster. Insert equation, okay. But I have to, okay, so it would be A equal cosine of delta theta plus times the identity matrix. So there will be times I, sorry, plus this 1 minus cosine of always delta theta And the product of E, so it will be, let's see if I can, so it will be, so there will be a vector, so it will be E times E transpose minus sine of delta theta times a matrix called E, where E, so if we add another textbook here, the matrix here is a 3 by 3 matrix that represents the cross product matrix of the vector of the instantaneous axis of rotation. So basically, if you let's write so it will be 0, 0, 0 in the diagonal matrix, and here you have minus E Z E Y and E X, and you have also E1, so it will be EX, or actually here there is a minus, and you have EZ here, and you have minus EY there. Okay, so what in principle we can copy this matrix here and determine the matrix A that we have due to the Euler's theorem. So basically here will be a little bit long expression, so I will only write a few elements, but the reason why I want to like to show you that is in order to know how we were able to determine the attitude matrix in function as a function of the Quaternions elements. So this is, for example, the first element. Afterwards, you have EX times EY y minus cosine of delta plus E zeta sine of delta theta. So, and also the other term here I'm not going to write, but are the given by the multiplication, so the sum of these matrices, because this is the identity matrix with the diagonal element equal to cosine of delta theta. This is the matrix given by the product of E, ET, and this is the product of a sine of delta theta to this matrix here. So you can compute this matrix by yourself, but it will be pretty straightforward. And you can notice that since we have defined the quaternions as before, so that the Q is, so Q1, let me rewrite here. So since we have written that, for example, that Q1 is equal to EX times sine of delta theta, and so on. So it will be Q2 similar expression. So you will have Q2, Q3, it will be equal to Y and Z. And here will be only cosine of delta. So basically, if you take this expression of the matrix as a function of the instantaneous axis of rotation and the instantaneous axis of rotation, you can build this matrix as a function of delta theta and the element of the instantaneous axis of rotation. And since you were able to determine the elements of the quaternion as a function of Q1, Q2, Q3, and Q4, you can substitute this form so replace this form with the quaternion elements. And if you do some computation, matricial computation, you are able to indeed determine this expression of the attitude matrix. So this is an important thing because, as I told you, this expression of the matrix will be important, for example, in a method of attitude determination that we're going to see today. So this is only a refresh of the properties of the quaternions. If you have any doubt, you can read the appendix in the book by CD that has a brief description of the properties of the quaternions. But if you have any question, let me know. I will try to refocus on particular properties. So yesterday we concluded here. The conclusion was indeed trying to determine the attitude kinematic equation using the quaternion representation. The main properties of the quaternion that we have seen yesterday was indeed that a multiplication of matrix can be simplified by multiplication of quaternions, the one that we have defined early this morning and yesterday. So let's do an example. So as I told yesterday, if you have the state at two different epochs, so let's assume that at a certain time t, you have your knowledge of the quaternion, so you have a qt. And you want to determine the orientation at time t plus delta t. If you were trying to do the same problem for the position of a spacecraft, you know that you have to integrate the orbital equations in order to find the evolution of the state of the spacecraft. Here we have to do the same. The only difference is that we are not going to integrate the equations of the spacecraft orbit, but the equation of the spacecraft altitude. The quaternion enables a simplified computation because, as I told you, in order to obtain the attitude, so the orientation of the spacecraft at a certain time from here to here. So if you know, for example, qt, and you will also know the variation of the quaternions that occurred in these delta t by doing a simple quaternion multiplication of this one by this one, you are able to determine the quaternion at time t plus delta t. If we want to determine qt plus delta t, let's assume, for example, that the rotation that occurred in this delta t was indeed given by a certain axis of rotation, so E, that it is equal indeed to our omega versor. So it will be this omega dash, for me it's dash in order to show you that it's a vector, divided by the module of omega, where omega is indeed our delta, so basically is the angular rotation of the spacecraft at that instant. So we know that in that time the spacecraft, so the rotation of the spacecraft was only given by delta theta. So as we have written before, the quaternion is written as Q4 equal to cosine of delta theta 2, and the vector part is given by the E times sine of delta theta, of delta theta. But delta theta is equal to omega times delta t, right? So we know that delta theta is equal to omega, so the instantaneous angular rotation times delta t. So we can write this expression in this way. Why we need to do that? Because as you have done for other problems, if you want to determine the partial derivative, so the derivative over time of the quaternion, you will do the difference between qt plus delta t minus qt. As we said, this form here is a product of quaternions. Okay, so basically this operation is a difference between quaternions, and this is the multiplication of this quaternion to the quaternion at instant qt. So I would like to be sure that you understand this formalism. So basically what here doesn't mean is that this quaternion here has, so the first quaternion is given by, so if this is the scalar part, so it will be cosine of delta theta, and the sine of delta theta, so this is delta theta. So let me write as before, it will be faster with the equations. Okay, so let's insert a text box. Okay, so that will be equation. So the first quaternion, that will be our Q delta T is equal, so it will be like a vector 4 by 4. So let's do it in this way. So here will be the cosine of delta theta. Okay. Okay, so the other three elements so it will be Ex sine of theta. Probably it's better if I had another slide, because otherwise it will be, so let's duplicate that. Okay, so this one will be indeed, okay, and it will be AY. So the other expression that I would like to explain through these, okay, perfect. So this is the first vector here. So this part here. The second part is similar, but is only given by 1, 0, 0, 0. And this is not Q delta T, but it should basically is this quaternion here. So when you do the difference between these two, of course you have what you've got in the next slide. So if you do indeed the difference between the two, what you get is a vector that it is equal to cosine delta theta half delta theta 2 minus 1, and this vector itself. What we are doing here is we are doing this difference divided by delta t, and you are doing the limit of delta t that tends to 0. So it means that when you do, when this one delta t tends to 0, also delta theta tends to 0. So this one tends to 1. So 1 minus 1 is equal to 0, and that's the reason why you have a 0 here. This one is not really affected because if theta is delta t is 10 to 0, this one is 10 to, to the angle. So you have that this vector is indeed the omega that we have written here. So this formula is here is exactly what I have written for this one. So at the end, the advantageous form of the kinematic equation with quaternions is that you can write the this equation as a pure multiplication of two quaternions. With the first quaternion that is given with the real, so the scalar part equal to 0 and the vector part equal to omega. And qt is the quaternion at time q time. Okay, so since we have seen, so that's the reason why I introduced this form of the quaternion multiplication. That in principle you can do as we have said before. But if you use a matricial form, since you know that A is equal to 0 from this quaternion here, you have that delta q over delta t, that is basically given by the limit of delta t that tends to 0 of this difference divided by delta time, it is equal to 1/2 of this matrix, that is the matrix for the quaternions multiplication, times qt. This matrix, indeed, is usually defined as big omega, that is a function of the instantaneous angular rotation. So this one is our omega of omega. Okay. This is a remarkable result because basically that enables to integrate the quaternion state every single time. And it would be really advantageous, for example, when we have specific sensors as the gyroscopes. Since in the next, today we're going to start the attitude determination, we are going to see that the sensors, so the type of sensor, can impact on the method that we can use for the attitude determination. So what you can see from here is that since the quaternion, so since the gyroscope will give us the instantaneous angular rotation of the spacecraft, there could be a useful sensor that can be used to integrate this equation. For example, we are going to see briefly. But when we're going to see briefly the multiplicative extended Kalman filter, you're going to see that we're going to use this equation in order to integrate the quaternion state. And that will be really helpful because, of course, every single time you're able to determine how the quaternion evolved. And so if you know how the quaternion evolved over time, you are able to determine how the attitude matrix evolved over time. However, this is important when you want to integrate the state. So in this case, the attitude state. So when what we are going to see today is that not always you need to do this kind of approach. So this is important, for example, when you have a gyroscope, because you have continuous measurement of the angular velocity, and you can include those measurements in the integration of the equation in order to determine the attitude every single instant. But there are other families of the attitude determination algorithm that do not need the integration of the attitude state. The first two, so the main two algorithms that they are going to see, one is called the TRIAD algorithm, and the other one is called the Wahba, so it's based on the Wahba problem. In order to introduce the problem of attitude determination, we have to do an historical introduction. The historical introduction is explain how the attitude determination problem evolved over time. So, as I told you, the equations, the attitude, the kinematic equation that we have seen here are very important when you want to integrate dynamically the attitude equations. But think about when we started to have the first attitude sensors. So for example, in the 1960s, when these two algorithms that I'm going to discuss about were introduced. In the 1965, if I remember correctly, or 64, it was introduced the TRIAD algorithm. So the TRIAD algorithm, it is called TRIAD not only because it's based on the generation of a triad of orthogonal vectors, but the TRIAD algorithm, it is basically the acronyms of the triaxial attitude determination. So this one stands for triaxial attitude determination. So it was the first attempt to determine the attitude of a spacecraft. So my question for you would be, do you think that for that, so at that epoch, they were, so what was the method that was used to determine the attitude of the spacecraft? So you think that was based on this complicated integration of the attitude equation, or was a simpler approach? So in principle, you, in order to determine the attitude of a spacecraft, how many elements, so how many parameters you need to determine the attitude of the spacecraft? This is a crucial question that it is basically the question that was answered when this triad problem was introduced. So you have an idea on how many parameters you need? I think that you already have seen in the previous course by Professor Colasurdo. So probably you have an idea on how many parameters you need. You want to?
I think we need 9 parameters. Am I right?
So 9 parameters is the number of elements of the attitude matrix. But so I will rephrase my question. What is the minimum number of parameters that you need to determine the attitude of the spacecraft?
It was 6, I think, and 3 of them was coupled with them. I'm not sure.
Okay, so no, it's not 6, and I will explain why it's not 6. So actually, the minimum number of parameters comes from these. I know that it's not a beautiful drawing, but it can be explained from these sketch. So basically, our goal is to determine the attitude of the spacecraft from the body frame to a certain inertial frame. So what you can do, indeed, is to determine the vector, or in this case, the versor E, the instantaneous axis of rotation, and a certain angle that enables to put the body frames on top to the inertial reference frame. So since the element of, so the vector E is a versor, the independent element of this versor are only 2. The other element that you need is the instantaneous rotation. So you have another parameter. So it will be 2 given by the fact that you have a versor, E, plus another parameter that is delta theta. So the minimum number of parameter is 3. So in 1964, when the attitude determination was introduced, so was a main problem, the only sensor that were available, if I remember correctly, was, so since it was the attitude determination of an Earth satellite, was an Earth sensor and a Sun sensor. So the Earth sensor and the Sun sensor give you the position of the Sun and the Earth with respect to the body reference frame. For example, the OBF that we have seen before. But you also know the position of the Earth and the Sun in the inertial reference frame. So if you use 2 objects, so you use 2 celestial objects or in general object, because you can also use stars that are known in the inertial reference frame and are also known in the body frame because you are measuring through your sensors, you have 2 versors, let's say. So you have two versors that give you the position in, for example, Earth and the Sun in the body frame that you also know in the Sun, in the inertial frame. Okay, so but that does not represent the minimum number of parameters, because as we said, to determine the attitude of the spacecraft, you need only 3 parameters. Here you are using 2 versors that have 4 independent parameters. Yes, so the first method indeed was already based on an overparameterization. So an overparameterization that is given by the fact that it was used for the first time 2 versors. And we are going to see in the next hour how these 2 versors are processed. The other method that we're going to see was, so this was indeed done in the 1964. I'm writing here a date, I'm not sure, but I think it was probably this date. The year later, Grace Wahba, so that's why it is called the Wahba problem, introduced an improvement to this method. So she realized that okay, but if we have multiple sensors, this method here is limited because we are only able to process 2 versors at a time. So we need to use an improved method to process multiple data points, so multiple observations at the same time. And the Wahba problem indeed faces that problem. And there are a few algorithms that are were designed to solve this problem. So Wahba in the 1965 introduced the Wahba problem, and many algorithms through now were indeed used to determine to basically determine this problem. For example, I think the first one was Davenport. That was done just after that this problem was posed, Davenport. But the one that we are going to use, and we have also a small demonstration, is regarding the quest algorithm. So what we are going to see to solve the Wahba problem is called the quest algorithm. But these two methods are able to process data or measurements that require observation at the same time. So basically, every single time that you have observation at that specific time, if you have only 2, you can use the TRIAD algorithm. If you have more than 2, you can use a Wahba problem. But if we need to use, for example, gyroscopes that have the measurement of the angular velocity of the spacecraft at different time steps, these two methods cannot really well suited to that.
What you read before the quest algorithm?
It's a Davenport. It's a Davenport. It's the name of the person that developed this method. However, I mean, we are not going to describe this method. It's only an historical information. The one that we're going to use is the quest algorithm. This is the one that is important. So these two algorithms can be grouped in one family. So the family of algorithms that requires observation at the same time. So if you have a star tracker, some sensors, and their sensors, indeed you can use those algorithms because you can process those observations at the same time. But if you need to use, for example, multiple observations with different integration time, these algorithms are not really well suited to do that. And we're going to look at the extended Kalman filter that is called multiplicative for the properties of the quaternion. So it is called MEKF, multiplicative extended Kalman filter, that enables the processing of observations at different time steps, at different integration time. But it's not only the differences between these two families. The other difference between these two families is that in this approach, we are only doing a static determination of the state. So this is a static, so this is an A, sorry, static determination. It's quite impossible to write with this trackpad, but I'm trying to do my best. So if you you're not able to read it, let me know as before. So determination. Okay, so means that you are able to determine the state every single time step. So you're not taking into account, for example, about the memory of the previous state. So every time you have an observation, you process the observations and you determine the state, but you don't keep track of the previous attitude determination. Kalman filter, as you already have seen before, so the Kalman filter has the possibility to propagate the information that you have collected before. And so what this approach enables is a filtering that takes into account to the actual observation that you are processing at that time step, plus the information that is given by the observation. So, filtering, this is a filtering of, and it is done, for example, to the tuning of the filter, right? You have seen that in the previous part of the course for the orbit determination, but the principle of Kalman filter is exactly the same. So, filtering of the a priori, so of the propagated information, propagated previous information, so previous information, and previous info plus the processing of the new observation. Okay, so plus new observation, and this is the main difference between these two families. So that's the reason why, and then we will have a break. What we are going to do, we are going to describe these two methods before the sensors, because these methods can always be used for star sensors, earth sensors, and sun sensors. When we are going to also introduce the gyroscopes, so at the end of this part, first part of the model, we also introduce briefly the multiplicative extended Kalman filter. And you're going to see some differences between the two methods. So let's start in 10 minutes, and we restart from the TRIAD algorithm. In the meantime, if you have any questions, we can discuss about that. So we made a distinction between the methods that we're going to use for the attitude determination. So the first two that we're going to analyze in detail, and that will be used, so that will be the core part of the attitude determination. The extended Kalman filter, I will give you an introduction to that, so don't be scared if you see in the full amount of slides, for example, 20 slides on the Kalman filter. I'm pretty sure that I will not be able to do all of them, but I think it is good for you to have an indication on how to implement a Kalman filter, okay? That could be also important for the homework, because probably this year, so since last year, I got many complaints about the homework was only on the control part, and the control part is explained in the second part of the module. This year, the homework, I can already tell you, will be a first part on the attitude determination and the second part on the control. And will be early May, so hoping that it will not going to overlap with other I don't know, homework that you have to do, or exams, or exercise. So let me know if that date should be fine for you. And as I told you, will be first part on the attitude determination. So probably you will need to use this method here. an optional task would be the Kalman filter, but it will not be mandatory. So as I told you, I will try to have at least part of one lecture on that because it is useful for your knowledge. Okay, so let's start with the main two active determination software or algorithm that we're going to use. So the TRIAD algorithm, as I told you, is an acronym of triaxial attitude determination. And since it was developed in the 1964, the only requirement that this method has is to have the measurement of so the position of an object with respect to the body frame. So two objects. So in the case of that when the method was developed were indeed the Earth and the Sun. So the spacecraft had a sun sensor and an Earth sensor. These two sensors give you these two vectors here. So W1 and W2 are the vectors of the two objects that we are trying to look at. So let's write down. So for example, this is the body frame. So as I told you, we consider the body frame and the optical bench frame the same. So basically we are assuming that we need to pass from the inertial reference frame to the body frame. So let's assume that is the OBF, okay? So the OBF means that we have an optical bench in which we have the Earth sensor and the Sun sensor. As we are going to see in detail in the next lecture, these two sensors give you the relative position of the these two bodies in the optical bench frame. For example, that would be the Sun. And here we have the Earth. Okay. So in our triad algorithm, this is W1 or could be W2. We're going to see that in detail later. But is the position of these two bodies in the optical bench frame. On the other hand, we exactly know where these two bodies in the ICRF, right? So let's assume that here we have the ICRF. So in this reference frame, the Sun is here, for example. So this is the Sun, and the Earth will be here, hoping that the relative position is the same, but anyway, as assume it is. And these two vectors in the ICRF are called V2 for the Sun and V1 for the Earth. I'm talking about vectors, but actually what we need are versors. So we are going to deal with only versors because we don't need to know the position. We only need the orientation of those bodies in these two reference frame. So what the sensor can measure indeed is only the versor. The relationship between these two vectors, it is easy because we know that if we want to go from the ICRF, from the ICRF to the optical bench frame, we need to determine the attitude matrix. So the attitude matrix is a transformation, as I already said before, the rotation matrix from ICRF to OBF. And this is the same for both vectors. So what we need to do now is to determine A for this matrix here. So these two are equal. What can create a problem? If the vectors, the versors W1 and W2 are wrong or as errors, of course, these two matrices will not be exactly the same. But also, the knowledge of the bodies that we are looking at in the ICRF can be affected by an error. So we have to be careful about that. And that will be dealt, for example, by the Wahba problem. So what, of course, has to be true is that W1 dot W2, so the dot, the scalar product between these two vectors should be equal in the OBF and the ICRF, correct? So we can use these two vectors, these two versors to determine the altitude matrix, because we know that the independent components of the matrix A are only 3. We already wrote that because if you look at this matrix here that I didn't complete, but probably I will do that so you will have on Google Classroom. It is only a function of delta theta, Ex, Ey, and Ez. But we know that the X, Y, and Z are not independent, so these metrics can be given but only 3 parameters. So here, indeed, we are over-parameterizing the problem because we are using 2 versors that have 4 independent parameters. To construct the matrix, we need to do this kind of procedure. So the triad problem consists in considering one of the 2 observations, the main observation. So assuming that W1 is equal to X1. And we construct a triad. So we compute W1, so the cross product of W1 and W2, because we need a triad, divided by the norm of the cross product. Okay. And the third direction, so the third axis of this triad is given by the cross product of the X1 and X2. Why we are doing that? Because since we want to determine a matrix that is a 3 by 3, we need to have a 3 by 3 system to invert. So we are using the information from the sensors that is given by W1 and W2. We construct this triad, and we do exactly the same for the relative position of those bodies in the inertial celestial reference frame. So it will be V1 for Y1, and we will do also the cross product of V1 and V2 to have Y2, and we do the third component to have a proper orthogonal triad. Once we have done that, we know that these 3 vectors are all tied to the attitude matrix. So if we multiply the attitude matrix by the vectors expressed in the inertial reference frame, what we get is the matrix of the versors of the triad expressed in the OBF. And so we have a 3 by 3 matrix. So the attitude matrix is given by this matrix computed in the OBF, also the OBF matrix, so our measurement from the sensors, and the one in ICRF. Of course, we know that this matrix is given by an orthogonal triad. So it is, we know that inverse is equal to the transpose. And so we are able to invert this problem and compute instantaneously which is what is the attitude matrix. Any questions regarding this method before going ahead? Okay, so let me see the chat if there are questions in the chat. Okay, no questions. I hope that it is clear, or it is completely fully not understood, but I hope that it is the first option. So now we can discuss about the weakness of this method. So of course, it was the first attempt to determine the attitude of the spacecraft. The first weakness indeed is that if we have multiple sensors with observation at the same time, we are not able to process all of them, but we have to select one of them. So we have to be careful about that, because of course, not all of the observation have the same precision. So for example, if we are, so we need, it is mandatory to use the TRIAD algorithm, for example, and you have 4 observation, and you know that 2, so 1 is the best observation. So in terms of quality, so that observation give you the best knowledge of the attitude. So let's say that you have 1 star tracker that only tracks a star. That is not really feasible, because as we're going to see, star tracker give you multiple observation. But let's assume that you have 1 measurement of the star tracker, 1 Earth sensor, and 1 sun sensor. So what you're going to do, if you want to use the triad, you have first of all to choose 2 observation from 3. And the other thing is that you are not going to use all those information, so all those measurements with the same weight. But when you do the triad algorithm, you are choosing that 1 observation is better than the other one. Because when you are going to construct the triad algorithm, you have that the cross product of W1 and W2 removes part of the information of W2. So the only way to have that all, so the 2 observations are weighted at the same way would be a very rare case. So the case in which you have the W1 and W2 are orthogonal. For example, if you have that the sun and the earth are exactly at 90 degrees from each other. In that case, you are able to have that all observations are weighted the same way. But if you have a relative angle, if you have in this case here, you have that part of the scalar product of W1 and W2 is completely neglected. So the scalar product W2 on W1 is not accounted for in this method. It's completely ruled out. You get rid of that. And that's the reason why the triad problem does not represent one of the main software, because you are going to lose information. Okay, so the other point is that, and that it is common for all the algorithm for site determination, you're not able to keep information, so keep into account the information of a previous state, but it's also in common with the Wahba problem. So the Wahba problem was introduced. Sì, yes.
Ma quindi c'è, se W1 e W2 sono ortogonali, questo metodo non si può usare?
No, So the question was, if we have a W1 and W2 are orthogonal, we cannot use. So it's the opposite. If we have the W1 and W2, you have the best scenario, because it means W1 times W2. So you are not, so you are using all the information for both sensors. You are not able to use W1 and W2 if are parallel.
Ah, okay.
Because in that case, the cross product is 0, and so you're not able to that. So that's another weakness that I didn't say. Thanks to ask me that. So,
excuse me.
You have. Oh yes.
Yeah, another question about the TRIAD very quickly. But what about building a further unit vector from X3 with the cross product X1 cross X3 in order to make X2 prime, let's call it that way, orthogonal with respect to X1?
So you mean that you take X1 is equal to W1?
Yes.
And you do X3 as X1 cross product to what? Because
I mean, for example, X1 is W1. Okay, I build X2, then X3, and then I build another unit vector in order to have an orthogonal, an orthonormal basis. In that sense, you were saying that W1 and W2 may not be orthogonal, but in that way we may have all unit vectors orthogonal.
No, but in this case are orthogonal, because what you're doing here is that W1, so what you're doing here is that you have W1. And so let's take this. So you get W1, right? Afterwards, you take the cross product of W1 and W2. So basically you are constructing a vector in this direction, for example. Okay, so you are doing an orthogonal norm, orthogonal triad. This would be X2. And you do X3 as the cross product of these three. So you are doing that. What I was trying to explain is that, let's do another sketch here. For example, okay, so yes, let's do this one. What I was trying to say is that this is W1 and this is W2. So what happens here is that this component of information, or actually is the opposite, because I mean, okay, because we are doing W1 cross product of W2. So this part here, this information here that is given by W2 is completely neglected, because basically it is already given by W1. The only information that you are taking is indeed given by the cross product of the two matrices. So it is basically the out of plane, in this case, out of plane component. So you are constructing an orthonormal triad. And that's the reason why that you are able to do the transpose of, so instead of the inverse, the transpose of the matrix. The problem is that you are not using all the information that is given by W2.
Okay, thanks.
Okay, so the main point here is that we are doing unit orthogonal vectors, but the problem is that we need to exploit all the information. Okay, so to solve this problem, and so to take into account that, for example, W1 is indeed more precise than W2, because, for example, one error could be, you know that W2 is less precise than W1, and you use to determine the triad by using X1 equal to W2. In that case, you are indeed doing a mistake because you are overweighting the observation that is less precise. To avoid this problem, it was introduced the Wahba problem. So the Wahba problem face exactly the situation in which you have multiple observation at the same time. So it is basically a simple extension of the triad problem. So instead of doing a triad, Grace Wahba proposed to to implement a cost function that depends by the difference between our W, so the versors of the relative position of the bodies, minus the attitude matrix times the knowledge of that body orientation in the inertial reference frame. So if you use the triad problem, basically what you can have similar results if you use that I goes from 1 to n. Let's ignore for now A1. So if you do the sum of the squares of the errors between W and minus attitude matrix and V, these sum of errors give you your positive cost function. So if you have two observations, you can have similar results with the Wahba problem or the triad. The main advantage here is that you can have a sum with multiple data, and data that however are collected at the same time, or at least at very short time differences, accepting that the variation of the attitude in that fraction of time is very small. So the problem is that I'm not still, so I already discussed how to solve the triad algorithm. The Wahba problem is not indeed the solution, but it's only the problem. So we have to introduce algorithm to minimize, in this case, this cost function. So we want to minimize the errors between the measured observation minus the observed observation and the known position of those bodies. So it's similar to what you have seen with the previous method for orbit determination, correct, right? The only difference here is that we have to take into account a certain formalism of the attitude matrix. And that's the reason why I spent last lecture on the Quaternions. Because the main advantage here is of Quaternions is to solve the problem by using the Quaternion formalism. So another important thing to discuss here is that, of course, since we introduce a cost function that depends on the attitude matrix, we can also include not only the differences between these two vectors, but also you can provide a weight on each observation. So if you know that, as I said before, the W1 is with a better precision with respect to the other observation, you can provide a larger weight, measurement weight, to that measurement. So for example, A1 will be larger than A2, A3, and the others. So this weighting of the observation is fundamental because, of course, enables the different weighting of the different measurements. So you are able to consider that not all observation provide the same accuracies. The important thing to keep in mind is that in order to provide an accurate weighting, you are not able to provide, for example, that since W1 is more precise than the others, you gave A1 equal to 1000 and the other one would be 10 or 0.1. So a reasonable criterion to determine the weight of those observations is that the sum of all those coefficients is equal to 1. So you can have a specific scaling of those weighting. That is advantageous because, of course, if you use huge numbers for the weight, you can risk to have numerical problems when you want to solve this problem. So if you take into account that, you are safe for these kind of problems because you are weighting correctly each observation, but also you're not providing possible sources of numerical noise or numerical error. Well, one of the main conclusions of the Wahba problem is that the Wahba problem is not really a minimization of a cost function, but this minimization of this cost function can be translated in a maximization of another cost function. Why we can do that? So let's use the matricial form of this expression. So we know that we have a sum of each specific element, of each specific vector. So you have here the norm of a vector that is given by the difference of the observed measurement minus the attribute matrix times the knowledge of the relative position of the body in a certain frame, in an inertial frame. Okay? In matricial form, this square, so this norm of this vector is written as the transpose of that vector times the vector itself. Let's write it just to be sure that we are on the same page. Okay, so let's keep it. I will write by equation so I will be faster. Okay. So I will write over there. So the subscript I means the vector of the body number I. So if we want to do that, the final the product of this one is a scalar, of course, because you have that, for example, your Wi is equal to so it will be Wx let me see, in order to don't use too many pedix. Okay, so let me see, because we will use also for the next computation. So let's okay, so I will use like that. So the superscript here is the component number, okay? So that will be I2 and I3. So if you do the transpose of this one, so it's not the square, this is the element number. So if you, oh, probably what I can do, okay, now let me, I don't like this formulation. equation. Let's do it like that. So it will be W1 I. Okay, so like that. So it will be easier to be also for others, for later computations. Okay, so that will be, okay, so if you do the transpose of this vector is a row vector. Okay, so basically what it means that if you do this one minus the attitude matrix times vi, you will have a row vector times this column vector. This one can be written as the, so when you do that, you have three main components. So will be the norm of the vector W and the norm of the vector attitude matrix times the vector V. So you will have 1 and 2, but by definition, we assumed that we are using versors, and so these two norms here, so these two norms here are indeed equal to 1. By definition. So 1 plus 1 is equal to 2, and since we have written that the sum of I from 1 to n of the coefficients ai is equal to 1, this will be indeed, so this first part here will be indeed the sum of I from 1 to n of 2ai. So you can bring 2 out from the sum and you get the 1 here. Similar approach could be done for the dot product, because this product of the two vectors, so the norm of this vector is given by the quadratic, so the norm of the two vectors W and AV, minus the dot product of the vector V, W and V and AV. So you know that the dot product of two vectors is indeed given by the transpose product, so it will be the transpose of this vector, so it will be a row vector that is given by W1I, W2I, and okay, also the other one, times the attitude matrix times the column vector that is given by the body in the inertial reference frame. So it will be V1I, V2I, and so on. Okay. These, so this part is equal to 1, as we said. This one is the function GA. So it is a function of the attitude matrix, and is a sum of that matrix. It is a sum of those observation products. So you have the row vector for the observed observable times the attitude matrix times the observed, so the observed body in the ICRF, in the inertial reference frame. So the minus GA represents indeed the final cost function. So the maximization of JA corresponds to the minimization of JA corresponds to the maximization of GA. So we are only going to look at this function. And now we need to use the expression that I said you before. So basically, here you have the sum of each observable from 1 to n. And each observation is scaled by the weighting factor. These metrics here can be easily represented by a trace of a certain matrix. How we can compute these trace? So let me include another slide. So probably I will use this one. It already have some. Okay, let me use this one. Oh, actually this one. Okay, so from here, new slide. So what we want to do is the maximization of GA. Okay. So let me start from the so what we need to do. So basically here it is explained briefly what you need to do, but just to give you a little bit more details about that. So that means that so this expression here is indeed given by a column vector, so a row vector that will be our W1E. So I'm not going to write I, but you know that is your I in order to don't have too many subscript. So that is the expression I'm going to write should be done for each observation, okay? So it will be, for example, in this case, like that. So for example, okay, so, and this is multiplied by the vector, the column vector that is it will be A11 times B1 plus A1 to B2 plus A3 B3, and the same thing for the second row. So that represents the expression that you have over there. 2, 2, 2, and you have a similar expression here. It will be 3, 3, and 3. So what you have here is indeed this form here. And this is always for the eye observation. So the main goal here, I'm not sure that, yeah, in 5 minutes I will be able to do that, but the main goal is to show you that if you took this expression here, you can, so this expression is equal to sum of m equal to 1 to up to 3. And also, for example, let's say, I will use a slightly different, no, let me use this exactly the same, okay, n. So let's use n. So from 1 to 3, okay, here you have to 3, and will be of W M A M N V N. So that's basically the same expression written in this form here. Okay, element by element. That is for each observation. So there is another sum on top of that. Okay, but this simple expression can be indeed written. So you can basically move this vector here to here. And this simple change give you the possibility to introduce another matrix, what we called B transpose. So B transpose, so let me, so you can test that basically these two expressions are equal. So you can move indeed the element of the matrix A and N on, actually move this element on your right. But if you do that and you want to determine this expression in a matricial form, this corresponds to, easy to be demonstrated, to V1 V1, V2, and V3. Okay, this one, it is equal to a matrix that I'm going to write. It is called B transpose. This matrix is indeed very simple to write, but very long to type. So will be D. I will just write a few elements, but it is very straightforward. So that will be diagonal matrix. Will be V2. And the same for D, so you can do V1, W2, and so on. Okay, so I will complete that and I will upload that. So the main point here is that this product here, so let me write as, so this product here is indeed our B transpose, okay? So the matrix, this sum here is only basically the trace, because it's the multiplication, and you can compute by yourself if you do A times BT, is the trace of A B transpose. And it is really important because this matrix, so B, it is called the attitude profile matrix. And the attitude profile matrix represents an important matrix that we are going to use when we want to solve the Wahba problem. Next Wednesday, we are going to discuss about the quest algorithm that is a way to solve these Wahba problems. So what we are going to do, simply, we're going to maximize this function, and we're going to determine the quaternion that maximize this function. So basically give you the minimum errors between the observed attitude measurements and the known position of the objects in the inertial reference frame. This problem, faced through the quest algorithm, will result in the eigenvectors eigenvalue problem. So we're going to find the quaternion that will solve an eigenvector problem. Anyway, this is a general expression for the Wahba problem. So the main concept that we have to keep in your mind is that the minimization of the cost function of the Wahba problem reduces to the maximization of this problem, and that enables the definition of the attitude profile matrix that will be useful in the computation of the quaternion that provides the best knowledge of the attitude. So I will stop here, and I will stop recording here. But I would like, if you have